Everyone, my name is Andrew Montrojo, and this is my midterm 3. Now, the problem we'll be dealing with today is going to be problem number 3, and this problem is a pretty standard Coulombic force problem. We take a charged particle with charge q and mass m, and subject it to the Coulombic force of a fixed particle at the origin that also has charge q, and we say this other particle cannot move. So the first part is going to be to write out Hamilton's equations for the system in polar coordinates, and then we'll be plotting it out in basis orbits for these four set of initial conditions. First thing we need to ask ourselves when doing this problem is, what is a Hamiltonian? And yes, we can write it out right here, but what this actually is, a Hamiltonian, if you think about it, Newtonian mechanics all describes everything in terms of forces. And so from here and from there, we can actually arise what's called a Lagrangian, where a Lagrangian, rather than determining everything based on forces, determines everything based on this sort of set of generalized coordinates instead. So we determine it based on a set of generalized coordinates of position and velocity for the Lagrangian. Well, the Hamiltonian is sort of an expansion of that. It's derived from the Lagrangian. It's not a Lagrangian, but it's similar to it in terms of that Hamiltonian is modeling our system based on a generalized momentum coordinate and a generalized position coordinate, whereas the Lagrangian will model it based on a generalized position coordinate and a generalized velocity coordinate. And this equation right here tells us how we get how we can calculate our Hamiltonian. So our Lagrangian, to start with, is actually just going to be our position minus, or kinetic energy minus potential energy. Kinetic energy, this is a very easy. This is just the exact form of kinetic energy we would use for polar coordinates. But what's interesting about it is that I've written it in terms of momentums. And that's very important to do here because we write our kinetic energy in terms of momentums because our Hamiltonian is all about basing things around using momentums. It's all about describing things in terms of these generalized momentums. Whereas if this was just doing a Lagrangian, I would just keep it as describing them in terms of their velocities. So we take our kinetic energy right here. Our potential energy, very simple to do. It's just the integral of our force dot with the dr. Our force here is just going to be kq squared over r squared, which we get from just knowing Coulomb's law. So we do that, we get our potential energy right here, Vr equals negative kq squared over r, and then we can just plug in everything into our Hamiltonian, and we get this equation right here. So now we can move on then to taking the derivatives of our Hamiltonian. We can differentiate our Hamiltonian with respect to each of our different coordinates. And we do that, say we take this dh by dpr, we find that the derivative of Hamiltonian with respect to its radial momentum is equal to the derivative of its radius with time, or how it's basically showcasing how its radius changes with time. Same thing with our linear momentum. How does our linear momentum change with time? How does our angle change with time? And how does our angular momentum change with time? In this case, you'll find here that our angular momentum doesn't change in time, meaning that our p theta is conserved, making theta what we call an ignorable coordinate. And now we can use these time evolution equations to create what's called a phase portrait to model how our system is going to change or evolve with time. A phase portrait is essentially going to be we're basically going to be modeling the time evolutions here. Each one of these little lines right here, I know it's so many lines, but each of these lines represents a different set of initial conditions here. And then when we go along the path of this line, it's actually telling us how the R and PR are changing with time. And that's why we love the Hamiltonian, because the Hamiltonian gives us these lines. They give us how these things change in time, which is so important here. So we take these four equations, so we take our four initial conditions right here, and we plot them on this little graph that I've masterfully drawn. I'm quite the artiste, you can see. But when we do this here, we get this little square right here. And then once again, we follow along each of these time evolutions here. We follow along this r dot and pr dot lines, and then after some time t, we get to a new point, obviously. And then we do this for each of these four coordinate points here, initial conditions, and then we get four new points. But these four new points will form a new quadrilateral. But the interesting thing about this new quadrilateral, that according to Liouville's theorem, that these two quadrilaterals have the same area, meaning that we can use that fact heavily to help determine more things about our system. So if you knew all the initial conditions here, but you only knew the results of say 3 of them, you'd be able to calculate the fourth based on the fact that you know what the area needs to be, or you'd be able to have some idea of what it needs to be. Well, thank you for listening to this. I hope everyone's learned something, and everyone has a great